Okay, so welcome back to the CS492D diffusion models and their applications. So last time we started to discuss some more kind of some application, the ideas in terms of like how we can utilize some kind of the pre-trained diffusion models for some kind of the editing or some conditional generation these setups, and also how we can basically enhance some kind of diffusion models in terms of that. It can also take some kind of some extra information, like some kind of conditions to generate some kind of something. So for example, like if we want to generate some kind of the images that are aligned with some kind of the texts or the labels, then how we can basically make this kind of the conditional model using the noise precision network was basically the idea that we were discussing last time. So we mainly discussed like two simple the ideas, which was the first one was the classifier the guidance, which is basically assuming that now we're having some kind of the pairs of the image and also the class label corresponding to each of the images. And here the question is that how we can also improve the quality of the generation by utilizing this kind of some extra information coming with some kind of the data set we want to generate. For those kind of the cases, like what we could do was that from this kind of the noise prediction, the part, we could basically decompose the noise deformulation into the two terms. And the last one is basically involving basically the information from coming from the given the class labels. So for this kind of to model this core function for this specific the conditional distribution, we could consider basically training a classifier in terms of like calculating the second term. For the complex schedule with the gas factor, where will we find the gas factor recording? So the gas factor will be also recorded, and also the recording will be posted on the same web page. So you can also join the same Zoom link. Everything will be the same with the regular lectures. So if you also have some kind of the conflicts with the gas lecture, just like send a message to me or our TAs on the Slack. And also the kind of the downside of the classifier the guidance was that it basically requires to train a XRD network, which is the classification network. And also this can be also applied to the only for the cases like when the extra input is the class tables, right? So the idea that was basically invented to basically improve the classifier the guidance was the classifier free guidance, which is basically not making any kind of extra neural network, but basically having our the noise precision the network to be able to basically take some kind of the extra input. And we also basically could enhance the given the condition in terms of basically doing some kind of extrapolation in terms of that we are training the noise prediction network both with the input the condition y here and also introducing some kind of the null label, which is the unconditional case. So by basically having this kind of like some linear combination with some kind of the weights, the omega here, we could basically enhance this kind of the given the condition. And the interesting thing was that this idea now can be applied not only for the class labels, but for the many other cases, like whether the input is the text description or some kind of the other images, or even the audio for many other kind of things. We could consider using this kind of like simple the idea of like utilizing the CFG, the classify free guidance. So you might also notice that some of the course projects are also about some sort of the conditional generations. For those kind of the cases, the easiest way to basically convert, making some kind of the diffusion model would be basically utilizing this idea, the classify free guidance, while there can be also many other the ideas that we can also make some kind of the better the diffusion model. And then also in terms of like, having some kind of efficient neural net that can handle some very high dimensional the data. The idea was basically also using the latent diffusion, which is basically like mapping all the given data set into the latent space, and also the training our the noise predictor in that specific the latent space. So we can also see that like all the kind of the well-known the pre-trained image diffusion models and also the video diffusion models are typically the latent diffusion the models, which is basically doing some kind of dimension reduction of the data into some kind of the low dimensional the latent space. So for those kind of cases that we could also consider basically incorporating some kind of the input condition. And in terms of like the way that we are basically feeding this like the condition, the input into the neural network, we can consider basically utilizing the cross attention model in terms of like computing the query key and the value, especially the key and the values from the given the input condition. So these are basically some kind of the design choices of the neural net, basically the implementation, but also what we are going to see in the next guest lecture is basically how we can utilize this kind of some attention information for many kind of some applications. So we're gonna get into that into the guest lecture. And then we also started to discuss some kind of the ideas about some fine-tuning based models. Like one of the example was basically the control net. So this was the case that like how we can convert a pre-trained the unconditional diffusion model into the conditional diffusion model, especially when the case was basically where basically all the outputs and also the input conditions are both the images. So for those kind of cases, like when you have a pre-trained unconditional the image diffusion model, which has been trained with the like 5 billion images, how we can basically convert this into the conditional model by having like way smaller the scale of the data set, like 100K the input and the output the pairs. And the idea for that is basically like utilizing the information, the knowledge basically learned by the pre-trained the encoder in terms of that we are also having the extra the encoder for the conditional input while basically copying everything from the pre-trained the encoder the network. And in terms of like doing some sort of the fine tuning with the small number of the parameters, we also discussed the idea of the zero convolution. So by basically having this kind of like zero convolution both for the input and the output of the each of the layer, we could basically have some very few number of the parameters that can help us to basically gradually like making the neural network to be adapted to the conditional the input. So this was basically the basic idea of like utilizing some pre-trained diffusion models based on some like fine tuning with the conditional degeneration. And also similar idea could be applied for some kind of the some personalized cases. Like if we want to generate some kind of images that is basically somehow making the images into some specific style, or basically making the images include some of the specific object or something, then how we can basically personalize the pre-trained diffusion the models. And for that, we could also consider using the idea of the low-rank adaptation, which is kind of similar with the control net in terms of that we are making some kind of the extra difference, but which is not the case of like taking so many kind of the additional the condition. Basically, it's taking the same input and also making the same output. And also the idea of the low rank adaptation was to basically having some kind of the bottleneck layers in the middle of some kind of the extra branch in terms of that we are shrinking the dimension of the some kind of the data in the intermediate kind of the variables in terms of that we can also reduce the number of the parameters in the neural network while basically making the fine tuning to be more the efficient. So these are all the ideas. And the assignment 3 will be basically about like implementing some part of like those things and also like playing with some kind of the pre-trained diffusion models for the some conditional generation and also the personalization. Any questions on this? Cool. So before we start the session for the assignment 3, I'd like to briefly just like wrap up the things that we couldn't discuss last time, which was about some kind of like zero shot the applications. So the control net and the LoRa was some kind of the ideas about like fine tuning some pre-trained diffusion models for some specific the applications. But here the thing is that even without like doing any kind of fine tuning, can you also utilize the pre-trained diffusion models for the editing or some kind of in-painting kind of the tasks? So basically here what we want to do is basically that we are having some kind of the condition, which is like, for example, like let's say like we are having some kind of the strokes drawn with some kind of the over some kind of images. So let's say we are on the left-hand side. The first row is basically some kind of the input image. And we are adding some kind of a stroke, like in terms of that, for the first one, we want to remove the doors here. And we also want to basically color the hairs a little bit in the second column. Basically adding some kind of the user input in terms of that we are kind of like breaking the reality of the images. So once we basically add these kind of like strokes, then the images become like unrealistic in terms of that we are having some kind of these strokes, but basically giving some kind of the guidance in terms of that. Now we want to basically color the part of the hairs into the yellow, where basically we want to remove some kind of the parts of the images into the specific color, basically giving some kind of the guidance into the images. And here the question is that how we can convert this kind of the slightly like unrealistic images with some kind of user inputs into the closest the realist images that you shown in the last row. So these are some kind of examples of the image editing. And we're also going to see many other techniques that can do kind of the same thing. So what we are also going to discuss for the last week, the next week, will be about basically solving some kind of the inverse problems. And we're gonna also get into the ideas for that. And the one is basically also about the in painting, which is the case that we are having some kind of the mask over the images that we want to basically fill that part. So let's say like we are having some kind of the input image and we are basically having this specific region. And we want to basically generate the images for this specific region, the foreground region that we say, while basically preserving the background region, the information in the other regions. Then we're gonna see that we are making some kind of some realistic images, which is preserving the parts that are not basically included in the mask, while basically making some of the changes in the foreground region. So this is basically example of the in painting. So those are basically some of the applications that we can basically try to solve using some kind of pre-trained diffusion models without doing any kind of the fine tuning. And the idea is like very simple. So we're gonna start this kind of like very simple idea for today's lecture. And from the next week, we're gonna get into slightly more like some kind of the advanced the techniques that is not just like tuning with some kind of the neural architectures, the neural net, but more about basically utilizing the diffusion process in the diffusion models. So the basic idea for the editing on the left-hand side is like actually it's like just very simple. It's just nothing but basically so yeah, these are some kind of the more examples that we are also having this talk the paintings. The first rule is basically the input. So we are starting from here, from the first rule and making some more the realistic images that are close to those kind of the unrealistic images. And the idea for that is actually extremely simple. So it's nothing but basically we are just like performing the forward process, basically perturbing the given images a little bit by with some kind of the small amount of the time step, and basically running the reverse process again from the perturbed images. So if we think about the diffusion models, like these are all about basically like, adding some kind of the noise into the realistic images in a way that like all the images are basically mapped to the samples of the unique Gaussian distribution, and then running the denoising process again in terms of mapping back to the original data point. And here, basically, the simple idea, there's basically without any kind of the theory for that, is that we can basically consider adding some kind of the noise into the realistic images, and then basically mapping this back to the realistic images by just like running the reverse process. So what we can basically observe is that depending on the times of like basically adding the noise, we can see basically some kind of the trade-off. Basically, what this means is that as we basically add some kind of the noise with some kind of the larger amount of the time step in the forward process, and also the running the reverse process for the longer time, obviously we're gonna get some kind of the more realistic images. So if we like think about basically the forward process that we discussed last time, if we basically run the forward process for the entire time step, whatever images that you have, all the images will be mapped to the points, the data points of the unique Gaussian. And all basically the points of the samples from the unique Gaussian distribution will be mapped to some of the realistic images. So if we want to basically get some kind of the more realistic images, then we can consider basically adding the noise in the forward process the more, with some basically the longer the time steps, and basically also running the reverse process back to basically the longer the time step. Then the downside is that the output that we're gonna get will be like very far from the kind of input that we are having. So those are some kind of examples that the leftmost one, this image is basically the input image. And actually basically add some kind of the noise for the longer amount of the time step and also running the reverse process again. We're gonna get completely different images like this. But actually, if we basically run the forward and the reverse process, not the full amount of the time step, but basically just like few amount of the time step, like the half of the whole the range, then what we can get is that we are still kind of getting some sort of the realistic images, which is still also close to the input image, the condition image. So we can basically play with some kind of the amount of the time step in terms of that we can get still kind of some realistic images while the output is not like being like deviated more from some kind of input here. Also, the thing is that if the time step is like too small, that then what we typically also get is that the output also becomes like unrealistic. So it's basically not making some kind of the big changes. So the output still becomes like some unrealistic images, while the output is like much closer to the input. So in terms of that, like all those kind of things, like we can consider basically picking some right amount of the time step in terms of that we are making some realistic images and also while making the output to be kind of close to the input image. Any questions on this? I don't quite understand the reduction dimension of the LoRa. The question about the LoRa, unit for the noise prediction already reduces dimension and the increased dimension. But so the LoRa is basically applied not for the entire neural network, but typically LoRa is also applied for each of the layer. So for it's basically not having some. It also depends on like how we also implement the LoRa. But the typical idea for the LoRa is basically not just like having the like basically having the module not for the entire network, but for each of the layer. So if you think about that, basically we are having the like one basically linear layer in the neural net, which input dimension is like n, and also the output dimension is basically m. Then it might be so it's kind of like the same that we are basically multiplying n by m matrix into the input, the n dimensional the vector, and then we are applying some kind of the activation the function, right? So here the idea is that n by m matrix might be kind of the like two big matrix. So we are basically decomposing this like the big matrix into the basically very two shallow the networks with some kind of the intermediate, some kind of the values, which is basically D. So that's basically the idea that we are basically reducing the number of the parameters for each of the layer, while basically making some kind of the extra the branch. Does it make sense? Okay. Yeah, and also any questions for this like SD edit? Yeah, so this as edit is actually quite simple, the idea. Obviously, also there's no theoretical guarantees in terms of like how much we can get some kind of the realistic images and while also basically how the output will be close to the input images. So, but this is like very practical, the ideas in terms of that we can do some kind of like this kind of like diffusion process starting from some kind of the slightly unrealistic images and just basically performing the fourth and the reversive processes in terms of that we are finding some kind of the closest the realistic the data point coming from the basically the input, the unrealistic the data point. So as I said, like there's no guarantee in terms of like how the output will be close to the input and how the output will be realistic. But we can just like play with that in terms of like doing this kind of things. So there's a very practical the idea. And one more thing that we can also discuss for today is basically about like in painting. So let's say like as I mentioned in the previous slide, we are basically filling the region that we call it the foreground, which is basically like indicated with the mask here, while basically preserving the outside region. So the right hand side is like another example that we are basically preserving the hair parts, while basically filling the left part and also the most of the part of the face. Then we are basically filling the foreground region with some kind of the new face, while basically preserving the other parts. For those kind of the tasks, like how we can basically use the pre-trained diffusion model without doing any kind of the fine tuning. Obviously, we can also consider using some kind of the ideas like the control net or the many other things. But actually, even without like doing the fine tuning, we can also basically do this kind of the in painting. So the idea for this is also like quite straightforward, but this can be slightly more complicated. So basically here the idea for the in painting is that we are basically combining both the forward process and the reverse process. It's kind of like the weird, and also there's no theoretical guarantee for it here. But basically what we can do is that let's say we are basically running this kind of like the reverse process for the foreground region. So let's say the second row here is kind of the same, the typical the reversed process. Yeah, we are starting from the X capital T, the unique Gaussian denoise, and then we are basically gradually the denoising every step. But what we are doing is that when we are basically sampling the xt minus one from the given the xt, so this is basically just like the one step denoising, right? Sampling xt minus one from the xt. But we are not directly taking this like xt minus one. But what we do is that, so the foreground is basically being denoised from the X capital T, right? For the background, like what we can see is that it's the case that we are basically have some kind of the known the x0, the final the output, right? So basically what we eventually want to get is that for the final output, the x0, the output image will, we hope that the output image basically matches basically the background region with the given input image, right? So we can consider that this is kind of the x0 for the background region. So every step of the denoising, that when you basically sample the xt minus 1 from the xt for the foreground region, now what we do for the background region is that we also run the full process starting from the x0 from the given input to the xt minus 1. So we are basically getting the same the xt minus 1 sample at the time step t minus 1. But the foreground region, basically what we do is that we are sampling the xt minus 1 from the xt, basically running the like one step denoising. But for the background region, what we do is that we are running the full process, sampling from the x0 to the xt minus 1. Basically making some kind of the two different kind of the noise images at the time step t minus 1. But one is coming from the basically the x capital T, which is being like the denoised every step. And the other one is basically coming from the x0, which is given as kind of the conditional input. And what we do is that we are now basically compositing this kind of like two different xt minus 1 using the given the mask. So for the foreground background region, we are basically taking this image, which is like being like the full the processed. And for the foreground region, we are taking the images which is like coming from the denoising. So that becomes, this composition becomes our the next step, the xt minus 1. So this is kind of like interesting, the idea in terms of like how we can also combine the forward process and the reverse process for each of the part of the images in terms of that we basically enforce the background region to be like preserved while basically making some kind of the realistic images for the foreground region. So what we can see is that since we are already basically sampling the xt minus 1 from the input, the x0, as the t decreases into the time zero, we're gonna see that there will be not big kind of the changes in the foreground region because like this xt minus 1 is in the background region because like xt minus 1 is basically always being sampled from the given the x0. So in this way, we can basically preserve the background region to be basically the same with the given input, while still basically running some kind of denoising process for the foreground region. So yeah, again, it's like starting from the for the foreground region, we are starting from the x capital T, and each of the time step we are basically denoising like one step in terms of getting the xt minus 1. For the background region, now we are basically running the full process from starting from the x0 in a way that now we can get the xt minus 1 for the background. And then doing some kind of the composition based on the mask that we have. And that becomes our the final the xt minus 1 and basically repeat this process again. And you might also ask the question like, how we can guarantee that this kind of the composition of like 2xt minus 1 will be basically, we will make some kind of the, smooth images like with some kind of the same, the noise image for the same object. So obviously there is no such kind of the guarantee. So which means that actually this kind of the in-painting process can be broken. So I also strongly recommend you to try to implement this yourself and see what you get. So for most of the cases, actually, it kind of like works well naturally. But you will also see that there can be some failure cases because of the fact that we are doing some kind of the composition of the xt minus 1 here. And the composition can be some kind of some very random, some arbitrary, some bad sample of the xt minus 1. For those kind of cases, we get some kind of the very the poor the outputs. So the reason why this is called the repaint is that actually you can do some kind of the replay as well. So once you basically run this kind of the kind of the denoising process, if you somehow find that the denoising the noise inputs or the xt is basically not just like being good, then we can basically run the full process again in terms of like going back to the some kind of the larger time step and doing this kind of the process again. So there are some kind of the engineering tricks in terms of like improving quality. But in any case, like this is kind of the interesting the idea in terms of that by combining the forward process output and also the reverse process output, we can do some kind of some in-painting kind of things. using this kind of the pre-trained diffusion models, even without doing any fine-tuning, any kind of some modification into the some given the noise prediction the network, but by just like modifying this kind of the denoising process. So these are quite surprising the outputs in terms of that we are having some very random the mask, like really just like taking the mask for the mask of the face and making some kind of images like this. And also very some random the strokes here. And this might be kind of the some extreme the cases like which is it's not in painting, but it's more about the out painting now, basically the filling the outside region. And we can actually get some very random results, like making some very diverse outputs. And this is the case, like filling the half of the images. So yeah, so these are some kind of the very some kind of the applications of the zero shot the applications. And these are also using some just like combining some kind of the forward and reverse the processes. And the next week, we're gonna also discuss some more examples doing some kind of the zero shot the applications, which is not just like playing with some kind of the neural architecture or we like combining the forward the reverse the processes, but which will be more about basically really modifying the denoising process itself in terms of like doing some kind of the other tasks. Okay, so do you have any other questions on this? So if there is no more the question, okay, what if the size of the mask area enlarges as T increases? I think it could be more natural for, oh, I see. Yeah, I don't know. So actually we also haven't, I haven't seen any kind of the examples that, we are dynamically change the kind of the mask regions over the diffusion, the denoising the process. But this can be quite interesting. So yeah, we can see like what happens if we basically, dynamically basically it will enlarge or decrease the size of the mask regions. So that can be also interesting in some kind of the some experiments that we can try. A good question. Any other questions? Cool. So if you have more questions on this, please let us know on this Slack. And today, what we are going to do is that we are going to discuss the assignment three, which will be the case that we are switching the gear now. So these will be basically some kind of the cases, which is like focusing more on the applications. So what we are going to do is that we are now going to start to use some kind of the pre-trained diffusion models, and especially we're gonna based on the library which is called the diffusers, which is the some kind of library that we can use some kind of the some pre-trained diffusion models like the stable diffusion. So our TA, Yusung will explain about the assignment three. Okay, one second.